We are now going to learn to take derivatives of a few more special functions. That's sort of interesting because let me do a quick review and you'll see why in a minute. We recently learned how to take the derivative of natural exponential functions. Let me do just a couple of quick examples. Actually, I'm going to write down the steps we did, and you'll see why in a minute. So here's a natural exponential function. Natural exponential function means the base is this e, right? Now, if you recall, the steps were copy the exponential function and then multiply by the derivative of the exponent, right? So, of course, 4 is just a coefficient tags along. So the derivative of e to the 6x, you copy e to the 6x, and you multiply by the derivative of the exponent, which in this case is 6. So if we simplify this, the derivative would be 24e to the 6x. And we could do another one a little more complicated. How about if our function is e to the x squared plus x, and we want to take the derivative? First step, you just copy, rewrite the exponential function, and you multiply by the derivative of the exponent. The derivative of x squared plus x is 2x plus 1. And there's your derivative. Now, what we're going to learn today is to take the derivative of not natural exponential functions, but just exponential functions. In other words, all the exponential functions where the base is not e. So for example, y equals 10 to the x. F of x equals 4 times 2 to the 3x. Or maybe even a little more complicated. F of x equals 5 x squared plus x. So the key here is, for all of these, the base is a number. Over here, the base is always e. And it's like we have sort of some special rules for natural exponential functions. So now let's figure out how to take the derivatives of exponential functions where the base is just like a number. And what's interesting is it's actually the first 2 steps are the same as we have over here, except there's one extra step. So I'll just write it out here and then we'll maybe do these examples. Same first step over here. You copy the exponential function. Let's just do this first one. So y equals 10 to the x. The derivative, copy the exponential function, 10 to the x. Second step, same as over here. Multiply by the derivative of the exponent. So in this case, the exponent's x, derivative of x is just 1, which I multiply by 1. So what's interesting, the first two steps are the same. The difference is there's a third step here. And it's sort of funky, but here's the extra step. You multiply by the natural log of the base, right? So here's my original exponential function. The base is 10. First step, rewrite the exponential function. Second step, multiply by derivative of the exponent. Third step, multiply by the natural log of the base. Natural log. The base is 10, so you multiply by the natural log of 10. So, not too difficult, because you've already done the first two steps when you learned how to take derivatives of the natural exponential functions. All you do is add this third step, which looks a little crazy, but it's easy. It's not difficult. It's always a natural log of the base, and you multiply by it. Let's do these other two examples real quick. So what if I had 4 times 2 to the 3x? I want to take the derivative. Well, first of all, the 4 is a coefficient, it just tags along. So now I want to take the derivative of 2 to the 3x. Exponential function, base of 2. First step, simply copy down the whole exponential function. Now I'm going to multiply by the derivative of the exponent. Derivative of 3x is just 3. Then this last step, then you multiply by the natural log of the base. In this case, the base is 2. So if you want to clean this up a little bit, 4 times 3, 12 times 2 to the 3x times natural log of 2. And this last one up here, a little more complicated. The exponent's a little more involved, x squared plus x. But if we just follow the steps, my base is 5. First step, rewrite, copy the whole exponential function. Then you multiply by the derivative of the exponent. Well, what's the derivative of x squared plus x? It's actually 2x plus 1. And then, last step, multiply by the natural log of the base. So multiply by natural log of 5. Looks a little messy, looks a little strange, but that's what it is. So really not too difficult. Let me do 1 or 2 examples from the book. Just a few more examples. Here's one. How about sort of like the one I just did. Y equals 7 x to the 4th plus 2. Just for fun, because you can start to get confused. What if I had y equals 4x to the 6th? What's the derivative of this? This, the base is your variable. Your exponent's a number. this is the power rule, right? The 4, the 6 comes down in front, 6x to the 5th. I'm just saying that because sometimes it gets confusing. An exponential function is when you have a variable in the exponent. Here, all you have is a number. So when you take the derivative, different rules. Just don't get confused. So right now we're working on exponential functions, which means there's a variable up here in the exponent. So simply copy down the exponential function, multiply by the derivative of the exponent. What's the derivative of x to the 4th plus 2? Well, 4x cubed plus 0. So it's just 4x cubed. And then multiply by the natural log of the base, which is 7. Now let's throw in a little throw your curveball, because now you have to sometimes use more than 2 of your derivative rules with one problem. For example, this one, x squared times 3x. We want to take the derivative of this. Well, it's almost like you're multiplying 2 functions. And remember, we use a thing called the product rule to take the derivative of this. So the way I like to do the product rule is I always write down the first sort of function times the derivative of the second function. So what is this here? This is an exponential function. So I'm now taking the derivative of 3x, which I now know. I just copy down the whole function. I multiply by the derivative of the exponent, which in this case is just going to be 1. But then I also multiply by the natural log of the base, which is 3. So this is actually the first half of the power rule. This is the first times the derivative of the second. So now I take the second times derivative of the first. Derivative of x squared is just 2x. And there you have it. Now you may want to, maybe you could factor out the 3x and an x and stuff, but I'm just trying to show you how to take the derivative. I'm not going to simplify now, just because I know you can do that. All right, so hopefully not too bad. So once again, you already knew how to take the derivatives of natural exponential functions, right? That's where e is the base. It's almost like these are special rules when e is the base. When anything else is the base, you sort of use the first 2 rules you learned over here, but then you add this third one. All right, hopefully not too difficult. Now, in the same way, there's another one we have to work on. We learned how to take the derivative of natural log functions. Once again, what were the steps? Let me write them down because they're so easy. You would write 1 over the, who knows what I called it before. Here's a technical term, stuff inside the natural log, right? And then secondly, so that goes in the denominator, and then you multiply by the derivative of, once again, the stuff inside the natural log. All right, you've done this before. So for example, the derivative of this, you put 1 over whatever's inside the natural log, then you multiply it by the derivative of what's inside the natural log. In this case, it's just 1. So this is 1 over x. How about the second one? What's the derivative of natural log of 5x? But 1 over everything inside the natural log, then you multiply by the derivative of what's inside. So derivative of 5x is just 5. In this case, it simplifies to 1 over x. Sort of interesting how these two are different functions, but the derivatives are the same. And then as we get a little more complicated, derivative of this, 4, it's a coefficient, tags along. Derivative of natural log of x squared minus 4. Once again, you put 1 over whatever is inside the natural log. And then you multiply by the derivative of what's inside the natural log. Derivative of x squared minus 4 is just 2x. So you would say this is like 8x over x squared minus 4. So this is all for natural log. And natural log is always written ln. If you recall, when I reviewed this, that means log base e. We don't write log base e. We call it ln, natural log. But that's what it really is. So now the question is, well, what happens to all the other bases? Log base 5 of x, or maybe log base 2 of 10x, or maybe common log, right? Log base 10 of, what would the derivative of all of these be? Now here's what's interesting. Just a few minutes ago, we reviewed taking derivatives of natural exponential functions and realized that these are the 2 steps. And when we went to do exponential functions, it's the same 2 steps plus a 3rd step. Well, we pretty much have the same thing here. The first 2 steps are the same. Matter of fact, instead of rewriting these, I'm going to do a same arrow over here, right? So the first 2 steps are the same. And then there's a 3rd step, which interestingly enough is the same 3rd step as up here. You're going to multiply by the natural log of the base. Well, not quite. You're going to multiply, it's actually 1 over the natural log of the base. So it actually goes in the denominator. So first 2 steps are the same with a 3rd step. So hopefully not too complicated. So this first one, we want to take the derivative. You put 1 over whatever is inside the log. Then you multiply by the derivative of what's inside the log. Derivative of x is just 1. And then you multiply by 1 over the natural log of the base. This is log base 5. So multiply 1 over natural log of 5. All right, let's do this one. Log base 2 of 10x. First step, you look at whatever's inside the log and you put it in the denominator. Going to multiply by the derivative of what's inside the log. Derivative of 10x is just 10. And then the third step, which is the new step, I'm going to multiply by 1 over the natural log of the base. This is log base 2, so 1 over natural log of 2. So this one would simplify, these 10s would cancel. 1 over x times natural log of 2. Now, one that's more complicated, it's more complicated, but you just follow the steps and it will work. So base 10, right? Common log, we don't put the 10 there, but log base 10 of x squared plus x. The derivative 1 over whatever's inside the log, multiplied by the derivative of what's inside the log. Derivative of x squared plus x is 2x plus 1. So those are the same steps we did with natural log, but then here's the third step. Then you have to multiply by 1 over the natural log of the base. This base is 10 here. So 1 over natural log of 10. All right. So hopefully, once again, not too difficult. Let me do one more example, and then I'll do a couple more complicated ones. And that's pretty much it. Let's just use this paper. How about, here's one that looks interesting. Y equals 8 log base 3 of 2x minus x cubed. So we want to take the derivative. The 8's a coefficient, so it just tags along. So the derivative of log base 3 of all this stuff. You put 1 over everything inside the log. Then you multiply by the derivative of what's inside the log. Derivative of 2x is 2. Derivative of x cubed is 3x squared. And then this third step, the new step, you multiply by 1 over the natural log of whatever the base is. Since the base is 3, 1 over natural log of 3. All right, let's just do a couple more. These ones can get sort of complicated. So for instance, how about this one? Y equals 4x times log base 5x. What do we have here? It's almost like we have two functions being multiplied. So if we want to take the derivative, we have to use the product rule. Okay, well, we know how to use the product rule. The way I do it is I write the first function, copy it down, times the derivative of the second function. So the derivative of log base 5 of x. Three-step process to get this derivative. First thing you do is you put 1 over whatever's inside the log. Then you multiply by the derivative of what's inside the log. Derivative of x is just 1. And then the third step is you multiply by 1 over the natural log of the base. So this is the first half of the product rule. Second half of the product rule is just you copy down sort of the second function. And now you multiply it by the derivative of the first function. This is a exponential function. Once again, 3 steps, right? You rewrite, copy the exponential function 4x, multiply by the derivative of the exponent, in this case, just 1, and then you multiply by the natural log of the base of your exponent. So this looks really messy, but that's the derivative. If I was doing this for homework, I would sort of, clean things up and make it all one fraction and stuff, but I'm just trying to show you how to take the derivative apart. I'm not worried about simplifying. Let's do one more that looks sort of interesting. How about this one? Y equals 3x plus 2 over log base 6 of x. And we want to take the derivative of this. So now we have like a fraction, like a function on the top, a function on the bottom. So hopefully you remember the quotient rule, which is the rule we have to use to take the derivatives of functions like this. So my little saying is low d high. Low meaning you just copied whatever is in the denominator, times d high means the derivative of what's in the top. Derivative of 3x plus 2 is just 3. Minus high, so I copy down what's in the top. D low, so now I'm going to multiply by the derivative of what's in the bottom. Here I'm taking the derivative of log base 6 of x. Now it's like a 3-step process to take this derivative. The first step is you put 1 over whatever's inside the log. Then you multiply by the derivative of what's inside the log, which is going to be 1. Then finally, you multiply by 1 over the natural log of the base. So this is actually the top part. And then you remember quotient rule is you square the denominator. So once again, I could clean this up a little bit. I'm not sure how much this actually simplifies, not a whole lot. It's just going to be messy. But once again, I'm not worried about simplifying. I'm just trying to show you examples of how to take derivatives. So once again, we're pretty much done now, but in summary, not that hard because you've already learned how to take derivatives of the actual exponential functions. So when you go to exponential functions, the same 2 steps, except you add a 3rd step. And then when we jumped over to looking at natural logs and all the rest of the logs, once again, for the derivative, the same first two steps as the natural log, but then you add this third step. All right, so I think once you begin to do some of these problems, you'll find it's not too hard. You just have to sort of keep things straight in your head and not get confused. All right, good luck with all of that.